Welcome back to the next video, everybody. Today, we are going to be looking at some basic elliptic curve theory needed for the proof of Fermat's theorem. We won't be looking at all or anywhere near all the elliptic curve theory we need, but we'll just be looking at the basics today. So what is an elliptic curve? An elliptic curve over a field K is a smooth, so think you can do calculus on it. Projective, think you can give it projective coordinates. Genus 1, think it's topologically a torus. Algebraic, think it's cut out by polynomials. K curve, think those polynomials have K coefficients with a K point. So there's actually a point on the curve that has coordinates in K. Okay. We can show that we may model an elliptic curve over a field K as a non-singular projective cubic equation over K in two variables. In fact, you can do better. By the Riemann-Roch theorem, every elliptic curve over K can be written in what we call Weierstrass form. It looks like y squared plus a1xy plus a3y equals x cubed plus a2x squared plus a4x plus a6, where all the ai's are in K. In fact, if the characteristic of K isn't 2, you can do much better. You can produce what I call a medium Weierstrass model, which is of the form y squared equals x cubed plus ax squared plus bx plus c, where a, b, and c are in K. And if the characteristic of K isn't 2 or 3, you can even do much better. You can produce what's called a short Weierstrass form, or a short Weierstrass model, which is y squared equals x cubed plus ax plus b, where a and b are in K. And all of these can be gotten kind of by applying a few successive changes of variables defined over K. And I'll say more about these changes of variables today, actually. One thing is these models don't have to be unique or anything like that. In fact, again, I'll say more about that in a minute. Okay, the converse is true. Every non-singular Weierstrass equation over K is a model for an elliptic curve over K. It's easy to check that a short or medium Weierstrass equation is non-singular if and only if this cubic on the right-hand side here has distinct roots. So that's nice. Okay, and so if I projectivize such a non-singular equation, this gives me the K point, which we call O, which has coordinates 0, 1, 0 on the curve. And so in this way, I obtain a model for an elliptic curve over K. I mean, you still have to make sure the genus is 1 and stuff, but this is pretty easy to do. So a good reference for this video, for all the stuff I've said so far and throughout the rest of the video, would be Silverman's The Arithmetic of Elliptic Curves, which I'll call S1 from here on out. The stuff I just got done talking about can be found in chapters 1 and 3, and I'll give more precise references for future material in this video as we go on. Okay, so this O here, by the way, we usually call it the point at infinity on the curve. And if you know projective geometry, you can probably see why that is. If you don't worry about it. It's just called the projective point at infinity. Okay, so let's let K prime over K be an algebraic extension of fields. If I give you an elliptic curve E over K, so K is the base field here, the set of K prime points on E, so the set of all points on E that have K prime coordinates is written E of K prime, and it's an abelian group under the addition law, collinear triples in E of K prime sum to 0. So if you have an elliptic curve, okay, and you have 3 EK prime points on it that are collinear, they'll sum to the point up here at O at infinity, basically. Okay. So you have to check this is actually a group law, which is not easy to do. Associativity is hard to check, but it's a group law, which is kind of amazing, actually. Okay. So 0 here again refers to the group identity, which is typically given by the point O above, that point 0, 1, 0, the point at infinity, although any rational point will do, but okay. An isogeny F from E to E prime of elliptic curves that are defined over a field K is a non-constant morphism of varieties that sends the identity element of this group to the identity element of this group. Okay, what's a morphism of varieties? Well, you can give these this risky topology. Once you give these a topology, you just ask that F be continuous, and you ask that functions on E prime pull back to functions on E through F. Okay. It turns out such a map has to be a surjective group homomorphism with finite kernel. All right. We'll say two elliptic curves E over K and E prime over K are isomorphic if there are isogenies F from E to E prime and G from E prime to E, so one isogeny going each way, such that F compose G and G compose F are both just the identity morphism. So it's kind of the definition you might expect. If K prime over K is a field extension, we'll say E and E prime are K prime isomorphic, or isomorphic over K prime, or K isogenous, or isogenous over K prime for that matter, if F and G are defined over K respectively, if F is defined over K prime. Okay, so I bring this up now, A, because you need to know all this, but B, because those changes of coordinates that I talked about earlier, taking an elliptic curve E over K in Weierstrass form to its successively shorter Weierstrass models, those are all actually K isomorphisms, and they better be right, or else all these different models that we came up with up here just represent different elliptic curves, right, as groups, which would be bad. All right. What's the discriminant of an elliptic curve? Well, I'll tell you what the discriminant of an elliptic curve given by a short or medium Weierstrass model, E over K. It's delta of E, and it's 16 times the product of the squares of the differences of the roots of the cubic on the right-hand side. Okay, the 16 is here for reasons that have to do with those changes of coordinates that I talked about a moment ago, and it's often not written at all. And so what we see is that the discriminant vanishes if and only if the cubic has repeated roots. If that is, delta of E vanishes if and only if E is not an elliptic curve. Okay, so let's suppose from here on out that the characteristic of K isn't 2 or 3. It's a standard fact that if the short Weierstrass model of an elliptic curve E over K is given by the usual, y squared equals x cubed plus ax plus b, where a and b are in K, then there's a very simple formula for the discriminant. It's just negative 16 times 4a cubed plus 27b squared. Okay, you can see brilliant.org for a great discussion about this. There is a notion of a discriminant for any an elliptic curve given by any kind of Weierstrass model, but the equation's kind of complicated for it, and so I won't write it here. You can see Silverman 1. Okay, global minimal models. It's a standard but kind of hard fact that every elliptic curve E over Q is Q isomorphic to an elliptic curve whose Weierstrass form, meaning which has a Weierstrass form, that has coefficients that are actually in Z, and whose discriminant equals what we call the global minimal discriminant of E, which is delta sub m of E, which is this product over primes P of P to the P-enic valuation of E. All I have to do to tell you the full definition of delta sub m of E is tell you what these VP of E's are. It turns out they're the smallest powers of P appearing in the discriminant of any Weierstrass equation with integer coefficients, which is Q isomorphic to E. So basically, this discriminant has minimal powers of all possible primes at once, showing up in any discriminant of any curve, Q isomorphic to E, which is pretty amazing that you can do that. It's even sort of amazing that you can even do it one prime at a time, but you can do it. Okay, so we call such an equation a global minimal Weierstrass model for E, and you can read about these in S1 chapter 8. How do you test for a minimal model, a global minimal model? Well, if all of the coefficients of a Weierstrass model of an elliptic curve E over Q, given in the usual long Weierstrass form, are integers, and the powers of each prime divisor appearing in the associated discriminant here are less than 12, then this model is minimal, globally minimal. Okay, that's pretty cool. We can also test another way, though. There's another important quantity you can associate to our elliptic curve, which we call C4, which is this B2 squared minus 24B4, where B2 and B4 themselves are given by equations in A1 through A6 that I won't write here, but you can see Silverman chapter 3. Okay. If E is given by the short model y squared equals x cubed plus ax plus b, then C4 is just negative 48a, for example. Okay. Now, if all of the coefficients of a Weierstrass model of an elliptic curve E over Q given in the usual long Weierstrass form are integers, and the powers of each prime divisor of C4 are all less than 4, then again, the model must be minimal. And it turns out, in some sense, the converse is true. In fact, you can talk about all of this stuff over fields of really any characteristic, and the converse is true over fields of characteristic other than 2 or 3. And that converse is, if I give you a minimal model for an elliptic curve E over Q, either the powers of all the primes dividing the associated discriminant are all less than 12, or the powers of all the primes dividing the associated C4 are less than 4. Unfortunately, it's not true that both of those things have to hold, though. Okay, and you can see S1 chapter 7 about this. How about changes of coordinates that preserve Weierstrass models? Well, if K is a field with characteristic not 2 and E over K is an elliptic curve, the only isomorphisms of E that preserve a given Weierstrass model of E and fix the point at infinity are those of the form x equals u squared x prime plus r, y equals u cubed y prime plus u squared s x prime plus t, where u, r, s, and t are in the algebraic closure of K and u is a unit. Okay, if E is given by a short model, the only isomorphisms of E preserving this kind of model and sending the point at infinity to itself are those of the form x equals u squared x prime and y equals u cubed y prime, where u again is a unit in K bar. This is dealt with in S1 chapter 3. Okay, so how about the J invariant? Let's let K be a field. Let's let E over K be an elliptic curve. The J invariant, J of E is given by C4 cubed over the discriminant of E. This is actually invariant under isomorphism of E, as the name suggests. That means it doesn't depend on which particular Weierstrass model for the curve I choose. If E is an elliptic curve over an algebraically closed field, the converse is actually true as well. Okay, so not only is the J invariant invariant under isomorphism in that case, in the sense that two different models have the same J invariant, but it's also true that two different curves with the same J invariant are isomorphic. So you can see Silverman 1, chapter 3 about this. So let's let K be a field. An elliptic curve E over K given in typical Weierstrass form satisfies the following properties. E is non-singular, so it's an elliptic curve if it has a K point on it, which it does once we projectivize. If and only if delta isn't 0, the discriminant isn't 0. E has a node, so I'm thinking of a cubic that looks like this in the XY plane, if and only if the discriminant is 0 and C4 isn't 0. And E has a cusp, so in the affine plane, I'm thinking of a cubic that looks like this, if and only if delta and C4 are both 0. And in B and C here, E only has one singularity, and furthermore, there are no other options. Well, of course, there are no other options, but that isn't clear until you've proven this. Okay, now, two elliptic curves are isomorphic over K bar if and only if they have the same J invariant. I told you that already. Let J0 be in K bar, then there is an elliptic curve defined over the field K adjoint J0, whose J invariant is J0. So that's nice to know. You can spit out elliptic curves with whatever J invariant you want, basically. You can see S1 chapter 3 for all this. Okay, how about reduction? We say that an elliptic curve E over Q has good reduction at a prime P if when the coefficients of a global minimal model of E are reduced modulo P, the result is an elliptic curve over FP. So you reduce the global minimal model, you get another elliptic curve. This is equivalent actually to asking that some Weierstrass model of E with integer coefficients reduces mod P to an elliptic curve over FP. And the proof is easy. It turns out that a prime P divides the discriminant of an integral model if and only if that model does not reduce mod P to an elliptic curve over FP. And since global minimal models have discriminant with minimal p-adic valuation for all primes P simultaneously among all discriminants of all models which are Q isomorphic to a given model, this is clear. So think about it. Okay. How about not good reduction? So what happens? What are the alternatives? We say that an elliptic curve E over Q has multiplicative reduction at a prime P if when the coefficients of a global minimal model of E are reduced mod P, the result is an FP nodal cubic. Okay. And a nodal cubic in general is a node is just a kind of singularity at which there are two distinct tangent lines. You have to think about what this means over FP, but it can always be given over any field in terms of Taylor expansions. Okay. So this is equivalent to asking that some Weierstrass model of E with integer coefficients reduces mod P to a nodal cubic over FP. Although I'll admit to you guys, I don't actually know the proof of this. I know it's true. I think you can probably prove it with the Tate curve, which we'll talk about in a little bit, but I don't actually have a reference for this. Okay, for the fact that these two definitions are the same, but I know that it's true. Okay, so how about, are there any other possibilities? Sure. We say that an elliptic curve E over Q has additive reduction at a prime P if when the coefficients of a global minimal model of E are reduced mod P, the result is a cuspidal FP cubic curve. Okay, and again, you're thinking about a singularity at which there's only one tangent line. You can talk about that over FP again by using Taylor expansions. Okay, so this is actually not equivalent to asking that some Weierstrass model of E with integer coefficients reduces mod B to a nodal cubic over FP. All right, and these are the only three possibilities. We either have good reduction, multiplicative reduction, or additive reduction. Now, you can take multiplicative reduction, so nodal reduction, and you can split it into two subtypes. So we say that an elliptic curve E over Q has split multiplicative reduction at a prime P if when the coefficients of a global minimal model of E are reduced mod P, the result is a cubic FP curve with a node, okay, whose distinct tangent lines, because that's the definition of a node, have slopes that actually live in FP, not just in some extension of FP. All right. If E has multiplicative reduction, which is not split, so those slopes don't both live in FP, then we say that E has non-split multiplicative reduction at P. Okay. If an elliptic curve E does not have good reduction at a prime P, we say that E has bad reduction at P. So multiplicative, so bad means multiplicative or additive. Okay. And then we say that an elliptic curve E over Q has semi-stable reduction at P if E has good or multiplicative reduction at P. So the reduction isn't too bad, basically. And we say that E over Q is semi-stable if it has everywhere good or multiplicative reduction, so meaning at every prime P. The reduction is good or multiplicative. Okay. The conductor of a semi-stable elliptic curve E over Q, N sub E, is given by the product over primes P at which E over Q has multiplicative reduction. Every elliptic curve over Q, and in fact over whatever number field, does have a conductor, but if E has additive reduction somewhere, the definition of the conductor becomes more complicated in general. I don't want to get into it. We're going to be discussing mostly semi-stable elliptic curves anyway. Okay. Torsion. So take a natural number n, define the n torsion of an elliptic curve E, let's say E over Q, written E bar n to be the subgroup of points of E of not necessarily exact order n and E. So remember, E is a group. So you can just look at all the points in that group of some order n, or of some order dividing n. That forms a subgroup by basic abstract algebra, and that's called the n torsion of E. In fact, this is just a general abstract algebra definition, although this notation is elliptic curve notation. Okay, what is the n torsion of E as a group? Well, let's let n be a natural number. It's a basic fact that if E over K is an elliptic curve with where the characteristic of K is 0, or if the characteristic of K is P and P doesn't divide n, then as groups, the n torsion of E is abstractly isomorphic to Z mod n Z cross Z mod n Z. Okay, what if the characteristic of K is P and P does divide n? Well, then if K is bigger than or equal to 0, the P to the K torsion of E is just isomorphic to Z mod P to the KZ, or it's the trivial group. And you can see S1 chapter 3 for this. Okay, uniformization. The uniformization theorem for elliptic curves over the complex numbers says that every elliptic curve E over C is a group isomorphic and biholomorphic to a complex torus, C mod the lattice generated by 1 and tau for some tau in the upper half plane H, and that the homothety class of the lattice, 1 tau, determines the isomorphism class of E and vice versa. Okay, actually, the uniformization is really only one half of one of these statements. But to me, you should just learn all of these statements at once, and then let's just call that the uniformization theorem. Sue me. Okay, don't sue me, but actually sue me metaphorically. Okay. You can see Silverman advanced topics in the arithmetic of elliptic curves, which I'll call S2 from here on out. Chapter 1 for more information on uniformization. Okay, and the really amazing thing is that there's a p-adic analog to this theorem due to Tate. So it's called Tate's uniformization, and here's what it says. Let K be a p-adic field, so just think K is the p-adic numbers if you want, with absolute value, bar, dot, bar, I don't know. And let K and Q star satisfy the p-adic evaluation of Q is less than 1, meaning if you like, Q is divisible by P to the K for some K positive, if you're just thinking K is QP. Then there is an elliptic curve called E sub Q over K, which is called the Tate curve associated to Q, given by y squared plus xy equals x cubed plus a sub 4 of qx plus a sub 6 of q. There are equations for these, but I don't want to give them to you. Okay, satisfying the following. The discriminant of EQ has a nice product formula. It's Q times product over n at least 1 minus Q to the n all to the 24th. And the J invariant of E sub Q has a great formula too. It's 1 over Q plus 744 plus 19688 Q plus blah, blah, blah. And you're guaranteed integer coefficients here, actually. 2, if L over K is algebraic, then L star mod Q to the Z is isomorphic to EQ of L as groups, and this isomorphism respects torsion. This is really where you're seeing uniformization, right? What did we say in the complex case? We basically said that E of C is isomorphic to C mod some lattice, right? So this is almost the same thing, except for you can't take the field L here. You have to take its units, L star. Okay, so that's the only real difference. 3, let E over K be an elliptic curve with J invariant at least 1 in absolute value. If you work that out, that just means E has multiplicative reduction at P. Okay. Then there's a unique Q and K bar star such that E is isomorphic to EQ. This is amazing. And the isomorphism takes place at worst over a quadratic extension of K. In fact, Q is in K, it turns out. And this isomorphism takes place over K if and only if E has split multiplicative reduction at P. If L is an extension over which this isomorphism does take place, then E of L is isomorphic to E sub Q of L, and that's isomorphic to L star mod Q to the Z. So this is not surprising at all, just based on what we talked about already, but let's write it to be complete. Okay, now let's simplify. Let's let K actually be the p-adic numbers. Okay, we have this isomorphism, phi, right? From Q bar star sub P mod Q to the Z to the QP bar points of E. This isomorphism satisfies sigma of phi of x equals sigma of phi of sigma of x to the delta of sigma for sigma in the local Galois group G sub Q sub P, which is just the Galois group of QP bar over QP. And what is this delta here? Well, it depends. It's a character from this local Galois group to plus or minus 1, and it's the trivial character if E has split multiplicative reduction at P, and the unique unramified character, the unique unramified quadratic character of the local Galois group if E has non-split multiplicative reduction at P. For a proof of all this, you can see Silverman 2, chapter 5. That there is a unique such character, by the way, follows from the fact that there's a unique abelian unramified extension of QP of each degree, which itself follows from the fact that the same is true mod P, i.e. for finite fields, plus Hensel's lemma to lift the result up to QP. All right, so Next time, we'll begin looking at the Fermat curve, and we'll start applying some of this theory to Fermat's theorem. So I'll see you then. Thanks for watching.